The next fundamental law of electrostatics is Gauss's law. Gauss's law says that if you build a closed surface surrounding some region of space, and you look at the electric field going through that surface, you can calculate how much charge is inside the enclosed region. Think of it this way. If you have a positive point charge, all its electric field vectors are pointing straight out. If you draw a sphere around that point charge, the surface of the sphere will catch all those outward pointing field vectors. So even if you can't see inside the sphere, you know from seeing those outward pointing field vectors that there's a positive charge in there. Similarly, a negative charge will result in inward pointing field vectors. And if the sphere encloses a collection of positive and negative charges, some of the inward pointing vectors will cancel with outward pointing vectors, but the total vector flux through the surface will indicate the net charge enclosed by the sphere. This is the equation for Gauss's law. The quantity on the left is Q enclosed, the charge that exists inside the closed surface. On the right, you have the integral over the closed surface of the electric flux density going through the surface, indicated by d dot ds. Now, we're introducing a new quantity here, d. d is the electric flux density, which is a vector field that is related to the electric field by the material response of the medium in which the field exists. For the purposes of this class, we will use a direct scaling factor. d equals epsilon E. Epsilon is a material property called electric permittivity, which we'll talk about a lot more later in this class. In a vacuum, the electric permittivity is the physical constant epsilon naught, which is equal to 8.854 times 10 to the negative 12 farads per meter. So for vacuum conditions, Gauss's law could also be written like this.